I'm excited to dive into dictionary learning. We'll explore the relationship between the original data, V, the learned dictionary, D, and the sparse coefficient matrix, X. Think of it like this. We're trying to reconstruct a picture, V, using a set of building blocks, D, and X tells us how much of each building block to use. I see the core of this problem is to understand how dictionary learning uses the dictionary and the coefficient matrix to reconstruct the original data. We'll examine several statements about how those relate. The core idea is that the original data, V, can be approximated by multiplying the dictionary, D, and the coefficients, X. V is approximately equal to D times X. This isn't an exact match, due to the way we constrain X. This equation says that V is approximately equal to the matrix product of D and X. This means dictionary learning aims for a close, but not perfect, reconstruction of the original data. The matrix X is sparse, which means most of its values are 0. This is a key feature of dictionary learning. It makes the representation more efficient and easier to understand. We need to pay close attention to the size of matrix D. The number of columns in D matches the number of features in the original data V. This ensures the multiplication in the core equation works correctly. This reiterates the point about X's sparsity. Most of its entries are 0. A crucial aspect of dictionary learning's efficiency and interpretability. The number of columns in D is the same as the number of features in V. This means that the dictionary is built from the same number of characteristics as are in the original data. This line simply introduces the notation used for representing data, which has n_samples rows and n_features columns. I won't need to do any calculations. I'll focus on the conceptual relationships. This question asks us to evaluate various statements in relation to the core equation of the dictionary learning algorithm. Statement A reflects the approximate reconstruction property of dictionary learning. V is approximately dx. Statement B suggests an exact reconstruction. This is generally not the case because of the sparsity constraint on X. Statement C highlights the sparsity of X, a key feature in dictionary learning. Statement D points out the dimensional consistency between D and V, crucial for the matrix multiplication to be valid. Dictionary learning is a method, I, used to approximate a dataset. I, break down the data into smaller, more manageable parts. This is your original dataset. I'll represent it as a matrix, which is just a fancy word for a grid of numbers. Think of this as a set of building blocks. I create to reconstruct your original data. Each block represents a feature in your dataset. This shows how much of each building block, from matrix D. I need to reconstruct each data point in the original dataset, matrix V. This equation means I can approximate the original data, V, by multiplying the dictionary matrix, D, and the coefficient matrix, X. It's an approximation, not an exact match, because I aim for sparsity in X, more zeros. The number of columns in D matches the number of features in your original data, V. I need a building block for each feature. I see D as a collection of basis vectors. Think of them as fundamental building blocks. We use these blocks to reconstruct the original data. The number of columns in D matches the number of features in the original data. Dictionary learning is a technique I use to find the best way to represent data. I break down the data into simpler parts, the dictionary, and coefficients that tell me how much of each part one need. This is the core equation. V approximately equals D times X. I use it to reconstruct the original data, V, by combining dictionary elements, D, weighted by the coefficients, X. Because of the constraints, we usually only get an approximation, not a perfect reconstruction. This is simply stating that the number of columns in the dictionary matrix, D, is the same as the number of individual characteristics or features in the original data. V. I'm using sparse coding. That means the coefficient matrix, X, is designed to mostly have 0 values. This is important for efficient data representation. This allows for a more efficient and concise representation of the data. The V matrix holds my original data. Each row represents a data sample, and each column represents a feature. Because of the nature of dictionary learning and sparse coding, I usually can only get an approximate reconstruction. It's rarely perfect. I see V as your original dataset. It's a collection of data points, each represented as a feature vector. Think of it like a spreadsheet where each row is a data point and each column is a feature. For example, if you're analyzing images, each row could be an image, and the columns could be pixel intensities. This simply tells us the dimensions of Vn_samples as the number of data points, rows in the spreadsheet, and N_features as the number of features describing each data point, columns in the spreadsheet. This is the core equation in dictionary learning. I'm approximating your original data matrix V as a product of the dictionary matrix D and the coefficient matrix X. This is an approximation because we use sparse coding technique to make it computationally efficient. Think of it like trying to build a complex image, V, using only a few simple building blocks, D, and knowing how much of each block, X, to use. Because we're aiming for sparsity, to have mostly zero values in X, we don't get a perfect reconstruction. So, the result is similar to the original data but not an exact match. This tells us the size of the dictionary matrix Dn_components as the number of basis vectors, our building blocks I'm using to represent the data. N_features is the same as in V. It's the number of features in each data point. This shows the dimensions of the coefficient matrix X. It tells me how many data points, N_samples, we have and how many basis vectors, N_components, I'm using to represent each point. Each entry tells you how much of each basis vector to use for each data point. This is important. The number of columns in D must match the number of features in V because each column in D represents a feature's contribution to my basis vectors. The goal of sparse coding is to obtain a coefficient matrix X with mostly zero values. This means I'm using only a few of the basis vectors to reconstruct each data point, making the representation more efficient and easier to interpret. Think of it like describing a complex picture using only a few key features. I'm using D to represent a set of basis vectors learned from your data. Think of them as fundamental building blocks. Each column represents a basis vector, and each basis vector is a feature vector itself. The algorithm learns these vectors to best approximate your data. This matrix tells me how much of each basis vector, from D, I need to use for each data point, from V, to approximate the original data. It has mostly zero values because we seek sparsity. I see dictionary learning as a way to represent data in a more efficient and compact way. Think of it like summarizing a long story. I want to capture the essence without all the unnecessary details. This is your starting point, the original data, like a collection of pictures. Each row represents a single piece of data, a picture, and each column represents a feature, color values of the picture. This describes the size of Vn_samples as the number of data points, e.g., the number of images, and Nfeatures as the number of features per data point, e.g., the number of color values per image. This is a set of learned, basis vectors. Essentially the key features I've extracted from V. I use these vectors to reconstruct the original data in a much more concise way. Describes the size of Dncomponents as the number of basis vectors I'm using to represent the data, and Nfeatures as the number of features, as per original data V. This matrix holds the weights, or coefficients showing how I combine the basis vectors in D to approximate the original data V. It indicates how much of each basis vector is needed for each data point. Think of it as a recipe. X tells me how much of each ingredient, basis vector, to use for each dish, data point. This describes the size of Xnsamples represents the number of data samples and Ncomponents as the number of basis vectors. This is the core equation. I am approximating the original data V using the dictionary D and the coefficients X. The approximately equals symbol means approximately equal to, because dictionary learning is not perfect. It's an approximation, not an exact match. Think of it like trying to rebuild a Lego castle from a set of partially mixed up blocks. I can get pretty close, but never perfectly match the original without a lot more work. This is the technique I use to obtain the coefficient matrix X. Its core idea is to get a matrix X that has mostly zero values. Why is this important? Because many elements of X are zero, making the representation really compact, efficient and faster in processing. The goal of sparse coding is to have most of the values in X be zero. This means we only need a few basis vectors to reconstruct each data point, making the representation more efficient. Think of a picture represented by just a few key features, not every single pixel. Because of the sparsity of X, we get an approximation of the original data, rather than an exact reconstruction. I see D as the dictionary. It's a collection of learned features, or basis vectors. Each column represents a feature, and we use these to represent the data efficiently. Think of it like having a set of building blocks. This equation is the heart of dictionary learning. It says that our original data, V, is approximately equal to the product of the dictionary, D, and the coefficients, X. We're trying to reconstruct V using D and X. It's an approximation, not an exact match, due to the way we make X sparse. The matrix, X, holds the coefficients. Each row represents a data point, and each column represents the weight of one dictionary feature for that data point. A value of 0 means that a particular feature is not used to represent that data point. This is simply our original dataset. V is what we start with, and we aim to reconstruct it using the dictionary and coefficient matrix. Dictionary learning tries to reconstruct the original data, V, using a small set of features. I use those features, defined by D, and their weights, defined by X, and multiply them to build an approximation of V. Because we force many values in X to be 0, sparsity, we don't achieve perfect reconstruction. Instead, we have an approximation. The equation V approximately equals dx highlights this, approximately equal to, relationship.